Today's speaker is Vladimir Smorigin, and the title is Group Homology, or Review of Group Homology.
Yes. Well, actually, I'm mostly speaking about group homology, but it doesn't. Yes. Yeah, let me start by going through the definitions concerning classified spaces, actually. Right, so let G be a discrete group. And so we can define a groupoid, this calligraphic G, which consists of one object, and the morphisms are just the arrows corresponding to the elements of G. Right? And then by BG, we will denote a simplicial set, which is a nerve of this category G. Okay, so more concretely, this is just a simplicial set with which is defined as follows. So BG0 is just one element set, and BGN consists of well, let's just say it's n power of G for n equal to 0. Greater than 0. Okay, and I mean the
phase. What is M?
M is the nerve of this category. So this is a group where we take its nerve, and I mean I just to state it more concretely, I wrote this down. And I mean the phases and degeneracies are as usual. So yeah, it will be something like this. So we just put an identity element at the right place. And for the faces, it works like this. So where I take the product, or just drop the first or the last element. So this is for, let's say this is for I equal to 0. This for I equal to n is just okay. So this is this simplicial set, and we have a geometric realization. So this is the definition. Geometric realization of this simplicial set is called the classified space.
Well, I think it's worthwhile to review briefly why the nerve of a category is a simplicial set and
well, I mean,
basically, what is the nerve of the category?
Yes,
let's start with that.
Yes, the nerve of the category. So zero simplest, I mean, it's just the zeroth term is just a one element set. I mean, no. This is for our group, but I mean, in general,
yes, in general.
Zero simplices are just the objects of the category, and the nth simplices are collections of n composable errors.
Yes, so collections of tuples of errors such that the target of each error is the source of the next error.
Yeah.
Okay, so now we have simplices of all dimension. What are the faces and the degeneracies?
I mean, they work the same way. So if we let me just rewrite this. So if we had this sequence of
yes, so suppose we have n composable errors, or n minus 1 composable errors.
Let's say then the degeneracy will work like this. So we just put at the if place
Yes.
identity.
The identity error, which is always there, and this gives us another sequence of composable errors, which is longer by 1. And so these are the degeneracies, and what are the faces?
And the faces, well, they work like here. So if we can just compose two errors,
we can always because the errors are composable, we can compose any two, and we get a simplex of dimension one less than the dimension of the given.
Yeah.
Okay. So basically, it works for every category, and if we take G as a category with one object and lots of errors, we get something, and the something is the classifying space.
Yes.
Okay. Well, this definition is a bit combinatorial. So, are you going to say something about the topological definition of the classifying space?
Well, I mean,
I also wanted to add that it is actually possible to avoid writing down these formulas and just say that we have a co-simplicial object in category of small categories given by the simplex, the collection of linear categories of length n, and then we can consider this nerve as just the home simplicial set from this co-simplicial object to our category, and then it is immediate that this is a simplicial set. Yeah.
Okay. Well, yes, I agree, but it's another fancy way of thinking about the classifying space. Let's not go for fancy. Let's go for non-fancy. What is another way to define? Well, I think the most down-to-earth way to define the classifying space is for discrete groups is to say that well, we have a contractible space on which G acts freely and moreover totally discontinuously, whatever this means, and the quotient then will be the classifying space. So, is there a way to make a connection between the simplicial definition and the topological definition?
well, this definitely is, but well, I'm not sure at the moment how to proceed with it. They should be the same.
Well, there's a similar model for EG. well, one place where one can find the explanation is the beginning of the book Homological of Lie groups and Lie algebras by Fagin and Fuchs. So, if anyone's interested, in the very beginning they explain the connection between these two things. Okay, Volodya, I don't think anyone.
No, it's just for me.
Okay. So anyway, if you don't know which book I'm talking about, please let me know, and I'll post it in the chat. Okay. Well, another way to look at the classifying space is to say that it's E.g. by G, and very often the simplicial model is terrible, as it often is, but E.g. is more or less tractable, and maybe we'll see a few examples today.
Well, yes, this interpretation will be more useful for us in what's coming next. But I mean, I just started with this.
Wait, I think we will need the notes. So let's not erase the notes.
Okay. So.
Okay. And moreover, I think we'll need them as PDF.
So yes, we have this classifying space for any discrete G. It's worth noting that so let's say that first that BG is KG1 space. So its fundamental group is G, and it is aspherical beyond that. And also this this here gives us a so this map is well so EG is a covering space, and importantly it is contractible, because we will need this later. So these two things are worth noting. And yes, so it's not a given definition. It's just an auxiliary definition, but I'll need to prove some technicalities. So it will be useful. And let's say, let's check the rules. So yes, so let's call a so let's call a a CW complex X with an action of G on X, which permutes the cells. So such a cell complex is called the G complex. And of course, EG is such an example. It's actually the only one which we'll need. And there are many other G complexes anyway. So
I also think that it is worth noting that usually G complex is the one where all stabilizers of cells are trivial. Otherwise, it becomes quite complicated. But maybe in your definition, it's not the case.
Sometimes people do consider complexes with an action which is self-commuting, but not necessarily free.
Yeah, but then you should like put some restrictions on the stabilizers so that it is somehow regular. But
normally people do make assumptions such as the Homological type of the fixed point set should not be too complicated. But I always had an impression that this is something people do because they're lazy. Normally, when the action commutes cells, there aren't any point set pathologies, so everything should work. But nevertheless, for example, when people define equivariant localizations, there are all sorts of assumptions that crop up. For EG, we definitely need the action to be free. That's for sure. And basically, today we're not going to go into more complicated examples.
Yes, that's clear. That's actually what I wanted to say up next. So yes, we will only consider free EG complexes, and I mean we will only consider EG. I mean, okay. Right. So I want to say that if X is a free G complex, that is the action is free. Then the chain complex, the augmented chain complex of X is a projective resolution of Z over the group ring of, and I mean so yeah, so this action induces an action of on the chains. This action is also free, so we'll have just a bunch of free modules over ZG.
Okay. So
Yes.
What is Z of G?
Oh no, so, Z of G is a group ring.
Okay. So Z of G is the group ring if this term needs an explanation, please let us know. Okay. What is epsilon?
Epsilon is augmentation. But I just wanted to fix an error, because what I said is not true. I mean, we need this to be a contractible. So we need this to be a contractible space so that the homology of this chain complex would be trivial. Otherwise, we won't get the resolution.
That's true. Yes. So we want the resolution to be a cyclic. Otherwise, it wouldn't be much of a resolution.
Yeah.
Okay. So we have a free resolution of Z, and this free thanks to projective resolution.
Yes. Right. Well, yes, in fact, I mean, I could have just, instead of giving this general definition, I could have just, I could have been talking about EG from the start, because actually what I need is the chain complex for EG well, it is again a projective resolution, just follows from the previous position, because I mean EG is a free contractible G complex. Okay. So.
Okay, so we have a free resolution, and why do we need?
Yes, I mean it's we will need. I want to use this fact to later prove. So I will give two definitions of group homology, and I want to just give a sketchful proof of why they agree.
Okay.
Yes. So another fact that we need, and I think I forgot to go for it. So yes, for let's just talk about BG. So for let me give a definition first. Yes, so let's so I will denote so let M be a so let M be a ZG module.
Which is the same as G module.
Yes. Then this thing will mean, I mean, it's called covariance.
Yes. So,
and
we have two functors from G modules to G modules. The functor of variance and Kelvin variance.
So this is just one way to define.
Okay, and what's so there is another way which is more explicit. Let's state it as well. So we take M, and then we version out the submodule generated by something.
Something like this.
Okay. Yes. So we versioned out by the submodule generated by the differences M minus GM, where M is inside capital M and G is inside G.
Right.
Okay. So this is one functor. And there's while we're at it, let's also define the functor of invariance, which is very similar.
Okay.
So instead of the tensor product, we take the home.
So home
over ZG or over G, which is the same from where to where.
Well, it's either from Z to N, from
Z to N, yes.
Okay.
And equivalent, this is the same as the subset of submodule of M, which is spanned by M such that GM is M. Okay. So now we know what invariants and co-invariants are.
Yes, and what to say is that so we have this and I claim that chain complex for in G the thing okay, as a probably yes is equivalent in the sense of they have the same homology, so they have homotopy equivalent to the chain complex of BG. Okay.
And by the way, let's also do the co-chain version, which is exactly the same with
no.
It's upper star, not lower star, but upper star.
Oh yes, I mean yes. Just
otherwise the version, the co-chain version is exactly the same.
Yeah.
So we need to put the stars on G upstairs, and this is it. Okay. Well, actually, we don't know what a model for EG is, but once we have it, it's straightforward to prove these two quantities.
Okay. So we'll just assume it for now.
Yes. Again, if you're interested, have a look at the beginning of the Hagen-Fuchs book, and it's explained there.
Yeah, but there's also an incredibly easy way to say this. We just need to take the groupoid of the action of G on itself and then take its nerve, and then it's a model for EG. So
hold on. What do you mean the action of G on itself?
well, we just have G as a set, and it acts on itself by multiplication, and then we take a groupoid of it, and it's a model for EG. Well, its nerve.
Well, as Vladimir explained, it's a model for BG, not EG.
No. If it acts on a point, then it's a model for BG, and if it acts on itself, then it's a model for EG. That's sort of intuitive, because you like have only one point in BG, and for EG you like deloop this point into several into paths between different points in G. So yeah.
Okay. So what Grisha is telling us, there's a category which is obtained from the action of G on itself, and the nerve of this category is a module for EG.
Okay.
Okay, so presumably the category is as follows. The objects are the points of G, and the arrows are elements of G. And there's well, it depends on whether one considers right or left multiplication. Let's choose one or the other, and then there's an arrow from H to GH in this direction. Grisha, is this the category you were talking about?
Yes, precisely. Yes, that's the one.
Okay. So if we take the nerve of this category, Grisha tells us then we get a model for EG I think if this is true, it's pretty straightforward to check. Okay, well, and then we have a model for EG, and once we take invariance and co-invariance, we get chains respectively co-chains of BG.
Yeah, so let us now discuss the group homology, and so there are several ways to define it. Let me start with the more algebraically flavored definition. So this okay, yes, so homology of G with coefficients in some ZG module M is defined as the ether over ZG yes, so what this means is that we take a projective resolution of Z over ZG, over the group ring, and then we tensor this with them over ZG, and then we take the ith homology of this thing.
Okay, so in other words, we consider the ith derived functor of the functor of co-invariance.
Yes.
Okay, so by the way, let's also define cohomology, which is basically replacing x by tools by x. Okay, so if we what does general nonsense tell us? if we want to calculate, not so general, moderate to general nonsense, what does it mean? Well, if we want to calculate the tour of two things, we are allowed to take the projected resolution of the first one or the projected resolution of the second one, and the results are canonically isomorphic. Now, what about the x? There are two ways to proceed. If we want to calculate the x from something to something else, we could take the projected resolution of the source or an injective resolution of the target. And again, the results are isomorphic. Well, we do have a projected resolution of z, which we saw on the previous slide. So to calculate the cohomology groups, we just take the Hom from this projected resolution to m, and there is no need to calculate the an injective resolution of m, which could be and often is very complicated. Okay, so we have two functors, the functor of covariance and the functor of invariance, and we derive those, and we get the group homology and cohomology.
All right. So I just wanted to compute a simple example. Alright, so let's consider infinite cyclic group generated by T.
Okay. So basically, there are cyclic groups for which we could use the projective resolution, and it's possible to get the answer.
Yes, well, yes.
So let's try to do this.
Okay. So yeah, this should be it. I mean, indeed, if we take this map,
what is T?
T is the generator of this group. So yes, this map is just taken on it here. We act on it by G or by T. And,
let's see. So for G equals Z, what is the group ring?
I mean, the group ring would be
okay. So the group ring is the ring of Laurent polynomials with integral coefficients. Okay. So the map from Zg to Zg is simply multiplication by t minus 1, where t is the variable. Is this correct?
yes.
Okay, so we have this map, and this map is very explicit. Okay.
Yeah, so one can see that this is an exact sequence. So what we do next is that we take this coincident. We take the coincident. So we just where's the color? Gosh, yeah. Anyway, what I want to do is just take the tensor format Z. result. Yes, and we consider this Z as so G acts trivially on this Z.
Yes.
So what we'll get after taking covariance is just this. Here we conclude that if homology of Z is
Well, it's not very surprising. We know that the classifying space is the circle as one, and the homology and the homology groups as of S1 is something we know.
yes.
Okay, and what happens if we take an arbitrary module? An arbitrary module, basically with an action of Z. What does this mean? Well, this means we have a module and some endomorphism of the module.
Well, I mean the coefficient module.
Yes. So suppose we have a Z module M, or more precisely a Z of Z module M. What does this mean? Well, this means we have an abelian group and some endomorphism of this module. And then basically we already know H naught. H naught is the zero derived functor, which is the co-invariance. Okay, but what is H1? Okay, Dima and Grisha, do you know the answer? So suppose we have suppose we have an arbitrary module, but we take G equals Z. We only have H naught and H1. Well, H naught is something we know, but what is H1?
Well, I mean, we can calculate the answer by taking this resolution and saying that it's the kernel of this sort of normal map, but I'm not sure if that's what you're looking for.
Exercise. H1 is the same as the model of invariance. H level 1 is the model of invariance, and H level 0 is the model of co-invariance.
Yes, but that's because we have the equation that the action is equal to the trivial action on the elements of the kernel, because it should be in the kernel of t minus 1.
Okay, okay. Well, first of all, let's write it down. So suppose we
Your sound is off. Alexey Gorinov, can you hear me?
So can you hear us?
Yeah.
Okay, so we had some issue with the microphone, but it looks like it's working now. Okay, so we yes, so we have h naught equal m lower g and h1 equal m upper g. Okay, so for symmetry, let's write the answer for cohomology. It's the same with zero and one and g moved upstairs. So h upper one z with m coefficients is m upper g. This is something we know. The zero derived functor is the functor itself.
So it
m
was
upper g. The zeroth cohomology group or module is the module of invariance.
okay. Yes.
So this is m upper g. And h upper one of z with m coefficients is m lower g. And well, it's not massively difficult to check it. Let's say it's an exercise. By the way, these formulas resemble the Poincare duality, which is one way to basically to prove those formulas. We know what do we know? We know h0, h upper 0, and h lower 0. This is something we know. And then we have the Poincare duality for cohomology with local coefficients, which gives us h upper, upper 1 and h lower 1. Why? Because the circle is oriented. So normally there would be some contribution from the orientation sheaf, but this sheaf is trivial, so basically we get the answer straight away. Okay. So this is one way to prove this would be to use the resolution, and another way to prove this would be to use the Poincare duality for the circle as one, but non-trivial local systems. Okay. Anyway, are you going to say something about local systems and local systems on PG?
No.
Okay. Then what I just said is safe to ignore by anyone who doesn't know, doesn't care about local systems.
Yeah. So yeah, so I just wanted to say so that was the point of the previous discussion about G complexes and stuff. That there's another definition, another way to define group homology and homology as the homology of the classified space. It's with integral homology here. And in fact, from what we've seen before, it's quite clear that these two definitions actually coincide.
Okay. Okay, and more generally, if we put an arbitrary m on the left, in the left-hand side, then in the right-hand side we would need to consider homology with coefficients in the representation, which is the action of pi 1 on n. Okay, so let me write it down. So let's say it's okay. Well, so we have this. What is it? Well, let's BG, CG, G. Okay. So what is the local system? Well, let's take EG. Well, let's say that G acts on EG on the right. So G acts on M on the left. So we have this thing, which can be viewed as a local system on G by G. And this is the local system we need to put here in order for this to work for an arbitrary module. Sorry. Yes, it's like it's now it's good.
Right.
Okay, so now we have calculated the homology and cohomology of G with arbitrary coefficients. It's well, it's something. It's well, it's the complete answer for at least one group. Are we going to see any more examples?
Yes, I mean, we can, in a similar way, compute the homology of finite cycling group. I mean, the resolution would be quite simple, also.
Okay, well, let's look at the answer. For finite cyclic group, the answer is more complicated.
So yeah, let me just first state the answer. Well, actually, I mean, I don't remember. It's been easier to write down the resolution. Maybe just let's just write down the resolution. Well, again, the T is the generator of
Okay, and
G,
what is M?
yes, M is
Okay, and what is the next map after M?
it's again T minus 1,
And
and
what
then it repeats.
And what is the next one?
The next one is N.
Okay, so it alternates between M and T minus 1.
Yes.
And what is small n?
What's what?
Well, there's a small n in the definition of the capital N.
Yeah, this is the same N as
Okay,
here.
so it's, the small n is the order of the.
Yes.
Okay. The way what happens if you multiply t minus 1 by n?
It should be 0. Yes,
Delta 0.
and
Yes.
that's exactly what we want.
Well, it's a sanity check.
Yes. And again, taking the covariance, we obtain something like this. So 0 again. Here will be just multiplication by n, and again it alternates between these two. So then the homology is this. So we have Z for I equal to 0. We have for odd I and 0 for even I greater equal to greater equal than 2.
Okay. Let's write the answer for cohomology.
Yes.
It's very similar, but not identical.
Yeah.
Okay, let's take it as an exercise. In degree 0 we get zero. We get z.
Yes.
And then the answer for even an odd I greater than 0 is the same with even and odd interchange, meaning we have z by n for even I and 0 for odd I.
You can just use the universal coefficients.
Well, yes, actually, it's one way to look at it. We consider we use the universal coefficient theorem, which allows us to deduce everything from homology. Or we could use the resolution directly and take the invariance and see that the answer is okay. Hi is z by n for even I, h upper I is z by n for even I, and 0 for odd I. Okay.
Yes.
What's the answer for if we take an arbitrary module? Let's start with homology. So suppose we have an arbitrary module M. What do we get? Фиша, Дима, помните ли вы ответ? Потому что я не помню.
Для когомологий сейчас.
Или для гомологии. В общем, пусть у нас циклическая группа конечная, и мы хотим посчитать гомологию по гомологии в произвольном модуле. Ну, кстати, понятно, что все будет циклическим, ну, глядя на эту штуку. Ну, в смысле не циклическим, а начиная с какого-то момента все периодично. Да, ну, потому что у нас чередуется n, t-1, n, t-1, n, t-1. Поэтому достаточно вычислить только первые две, а потом, ну или там первую нулевую, то есть нулевую, первую и вторую, где дальше он будет повторяться. Вот, но чему равен ответ?
Ну, вроде похоже на правду. Ну, в смысле, ну там надо взять вот тот же фактор по действию этого оператора нормы. Ну, в гомологиях, в смысле, и ядро, ну, понятно, ядро вот этой штуки, которая фактически дает просто инвариант.
Явно видишь, что это такое, кто не знает. Okay, so another exercise, calculate, let's take an arbitrary G module M, calculate H naught, H1, and H2 with of G with coefficients in M.
В общем, в когомологиях там такой ответ, что надо в размерности 0, понятно, взять инварианты, а в размерности, которая четная, надо взять фактор инвариантов по норме вроде, а в размерности, которая... в размерности, которая четная, надо взять фактор инвариантов по норме, а в размерности, которая нечетная, надо взять ядро нормы, фактор по действию вот этого t-1. Вроде, ну, короче, вроде там какого-то более хорошего описания нет. Я не знаю.
Ну, решение, но может быть действительно нет. Anyway, let's say it's an exercise. Calculate hi for I equal 0, 1, 2. This, well, for I equals 0 is, we already know the answer, 1 and 2. Okay, and the same for cohomology. H upper I and H lower. Okay. Okay. So at some point we need to have a break. Volodya, would now be a logical moment to have a break?
Yes, we can take a break right now, but I mean, I don't have much left to say. But we can.
Yes, well, let's have a break, and after the break, are you going to say something about the Homological special sequence?
I mean, not really. So the plan was to next calculate the homology of symmetric groups, and I mean,
the homology of symmetric groups is very complicated, so we'll probably not be able to do it in general.
Yes, not generally, but for I wanted to calculate homology of S3, and this is what was suggested in the notes, but I got stuck with it. So I mean, we could try to. So there was a strategy advised in the notes. I just couldn't carry through it. We can discuss this.
That's okay. So okay, we'll do that. S3 is already quite complicated. Anyway, let's have a break and then calculate some more examples or maybe say something about the about special sequences and so on. Okay, so let's have a break. Shall we say 20 minutes? Okay. Let me try to see. Okay, so for the next example, we probably need some spectral sequences. Let's see. Well, suppose we have a group G and a subgroup H. What, if any, is the relation between the classifying spaces? Well, first of all, if we have an EG, it's also an EH. So we could take EG and take the quotient by H, and the result will be BH.
Okay.
On the other hand, we could take EG and quotient by G, and the result will be BG. And we'll have a map from BH to BG, and it's a vibration, and the fiber is G by H.
Mm-hmm.
So this works for an arbitrary G and an arbitrary H. Now, suppose now H is normal.
Why is EG over H? Sorry? Why is EG over H is BH?
Well, because EG is contractible, and the action of H is free and moreover properly discontinuous. Okay. So if H is normal, then G by H is a group. And then we have another fiber bundle. Namely, we have VH. Sorry, VG goes to VG by H. And it turns out that the fiber is VH. And so if we turn this map into a fibration, the fiber is VH. So the second fibration gives us a spectral sequence, which is, and by the way, the first one does too, but the second one says the second one, and the spectral sequence of the second vibration is, well, by definition, the Zehr-Hofschild spectral sequence. So let's write down the E2 term of the spectral sequence. E2 PQ. Well, yes, let's do the homological version, which is H upper P of well, G by H. With coefficients in the local system given by HQ of H with coefficients in M, where M is the G model we start with. Okay, so so far so good. But there's one thing we need to understand. What is the action of G by H on the couple H comma M? Or well, there isn't. But is there an action on cohomology? So suppose I have a normal subgroup H, and well, it's sort of well, this formula suggests there is an action of G by H on the cohomology of H with M coefficients. But what is this action?
Yeah, but it's worthwhile noting that M is actually a G module, otherwise it doesn't make sense.
Yes, this is important. M is a G module. And the spectral sequence, by the way, converges to H2 plus Q of G with M coefficients. Okay. Now, now we want to understand the action of the quotient on the cohomology of the subgroup. Now, what is this action? From topology, we know that this action exists, but is there a group theoretic way to describe it?
I'm sorry, maybe I don't understand your question, but first of all, for purely algebraic reasons, we have the action of the quotient because the whole group G acts, and then like H acts trivially on its cohomology. But also topologically, it corresponds to like the action of the fundamental group in the fiber by loops or whatever. I don't know what.
Yes, exactly. So we have an action of G on the couple H comma M, which is basically given by the conjugation action on the H component and the given action of G on M on the M components. Well, let's write it down. So G acts on H comma M, and on the first component we take the conjugation action, and on the second we just take the usual the given action. Okay. Now the question is we do get an action of the quotient group if the group itself, the subgroup itself acts trivially. So we need to understand this part. Why does if we take an element of H as G, why do we get a trivial action on cohomology? Well, this is something Grisha mentioned, but why is it true? То есть группа тривиально действует значит, на своих когомологиях, значит говоря, значит, если в качестве G взять элемент подгруппы H, то оказывается, что действие тривиально на когомологии. Значит, не на самой группе, точнее подгруппе, а вот на когомологии. Ну, значит, замечательно, спросится, с какой радостью.
Ну, как бы есть несколько способов это понять. Из топологического определения ясно, что, в общем, фундаментальная группа не действует никак на гомологиях. Ну, либо можно сказать, что мы когда там тензорное произведение берем льхом, то вот как бы действие аннигилируется этим.
Так, ну, значит, хорошо, ну давайте, значит, Гриша, а можете ли вы писать? Давайте мы подробнее запишем и поймем. Сейчас, значит, сейчас давайте мы сделаем новую доску, в смысле новый лист. И так, значит, Гриша, если вы можете написать, попробуйте что-нибудь написать.
Да, секундочку, сейчас. Сейчас я отключу.
Если это технически невозможно, то тогда давайте не пробовать.
А можно я буду в своей писалке это писать, а не на доске?
Так, ну хорошо. Сейчас мы не хотим потерять. Давайте мы сохраним.
Окей, я не...
Значит, решит такой технический сбой, и у нас почему-то сейчас что-то пропало. Что у нас пропало?
Ну, значит, нет, там все, в общем-то, вернулось теперь, но вот не факт, что сохранились, доска сохранилась.
Ну, сейчас, давайте, доска, она, по идее, должна быть в директории документа по директории Zoom. Вот, значит, Homological. Так, сейчас давайте посмотрим. Значит, вот который из них PDF? Там есть PNG и PDF.
Так, это PNG.
Так, значит, PNG нам не нужен, а вот PDF.
Это
тоже
PNG. Здесь нет.
Сейчас, это очень странно. Это очень странно. Сейчас, подождите, давайте... Бред какой-то. Ну, хорошо. Сейчас, давайте посмотрим. Так, значит, конференция. Так, сейчас. И чего? Так, сейчас. Так, ну ладно, хорошо. В общем, давайте с этим потом разберемся. Так, сейчас. Значит, Гриш, готовы ли вы значит, что-то нам рассказать?
Ну, в принципе, почему бы нет? Да, наверное, я
Да,
совсем
давайте.
чего-то объяснить, наверное, попробую, да. Так, ну, собственно, я не знаю, насколько как бы это будет осмысленно, но, в общем, ну, во-первых, ну, просто, если у нас есть топологическое пространство, то и специальная группа действует на...
Let's switch to English.
Yeah, sure. Sorry. Yeah, so if we have a topological space, then its fundamental group acts trivially either on its homology with constant coefficients or its homology with local coefficients. So I guess I can write. Yeah. So
why is this?
I don't know. Can we use this fact, or should I prove it as well?
Well, if it's not too difficult, let's prove it.
Sorry. Should I prove this or no?
If it's not too difficult, then let's prove it.
Well, okay. So sure. One moment. Yeah. So I guess.
By the way, which action of by one turns out to be trivial? First of all, let's define the action.
Yeah. So the thing is that I guess for higher homology, it's possible to only define the trivial action because there is no relation in general between like homotopy groups and homology, but in lower degrees, obviously, we can define the action using the Poincare lemma, which states that this is the abelianization of the fundamental group. And so since the fundamental group acts on itself by adjunction,
by conjugation.
Yeah, but by, I guess, yeah. So G gamma is mapped to G gamma G minus 1. So yeah, so this clearly shows that the action on the first homology group is trivial because we take the abelianization, and in the commutator this action is trivial. And for higher homology groups, I guess we can either say that this trivial by default, or we can also say that well, we have the action of the fundamental group on higher homotopy groups, and we have the Fourier homomorphism, which is compatible with this action, and so the Fourier homomorphism annihilates the action of the fundamental group, and therefore
Fourier's homomorphism is neither injective nor surjective in general.
Yeah, that's right, but I mean it's just some justification of why it is natural to define the action on the higher homology groups to be trivial. But as I said, in general, there is no other way to somehow relate the action of however, wait a moment. Maybe I'm incredibly wrong here, but I thought that there is in general no good way to define the action of the fundamental group on higher homology, but maybe that's not true, and we can actually think of some construction. So yeah, so maybe just a moment. Yeah, maybe there is actually a way to do this. I'm sorry. So I'm deeply sorry. So maybe there is actually a way to define this action using the action on singular simplices. So okay, so I guess we can try to do the following. So we can try to define the action of the fundamental group on the singular complex of our space, once again, either with local coefficients or with constant coefficients, by saying the following. So we have a singular simplex here, and then it has obviously some base point here, and then we can use I guess the following. So one moment. So I guess we can try to do something like this. So we have Yeah, I probably don't exactly remember this construction, but there is clearly a way to use the Khan extension condition to apply the action of a loop of either the fundamental group or fundamental groupoid to extend to an action on a simplex. So yeah, that's yeah. So I guess it should be like this. So we have for a simplex we have for example NH01, and then since we usually assume the space to be path connected, we can assume that it is presented by one reduced simplicial set. So it has only one zero simplex. So all vertices are mapped into the same vertex. And then we can assume that we have an action of the fundamental group by applying this action to some fixed edge of the simplex and then extending it to a map from whole delta n by the Khan extension condition, since the singular simplicial set of the topological space is a Khan complex, or just by saying that we have a Khan complex by assumption. So yeah, okay. So we can extend the action of the fundamental group or fundamental groupoid on the singular complex by adjunction, and then we can. Then we need to see that if we have an action on a simplex like this, then it is homological to the initial simplex, and one moment, how do we do that? Let me think for a moment. Yeah. Take this difference, and then it should be d of something in high dimension. Yeah, I'm sorry if my presentation is not very efficient, because I'm sort of trying to recall it from the top of my head. Yeah, I'm sorry if I don't remember it.
Well, let's see. Maybe there is a simpler way to understand what we want to understand. Basically, we want to understand the following thing. Suppose we have a group and a group H and an H module. We want to know why H acts identically on the derived functors of this of the functor of covariance. Well, first of all, let's look at the functor of covariance itself. So suppose we have no, this one well, this one is invariant. Okay, so we have but let's actually it's for invariance the answer is the same. Meaning the action is yes. So the action is still trivial. Well, let's start with the zeroth derived functor. So we have okay. So we on the level of m, we multiply by g, by a small g, which is an element of capital G. What happens when we take an invariant and multiply by g? Nothing happens. And on the level of g, we take conjugation by g, but it doesn't really matter. Okay, so on the level of zeros derived functor, nothing happens. G acts trivially. Why does the same hold for all the higher derived functors? Does anyone have a suggestion? Значит, вот, на нулевых технологиях группа не действует. Значит, а почему она не действует на первых технологиях? Ну и на вторых и так далее.
Не, ну, сейчас. В смысле, это не потому, что мы можем как бы то же самое сказать для следующего члена из элемента.
Значит, да, значит, что такое когнология? Это, значит, результат применения функтора инварианта. The homology is the result of applying the functor of invariance to the to the hom. No, sorry. What do we do? We want to derive the functor of invariance. So we take hom g from z to okay. There are two ways. Here it's okay. So there are two ways to proceed. We either take the injective resolution of G, or the injective resolution of M, or the projective resolution of Z.
Yeah.
We could do that. Okay, so okay, so written in this way, basically we have on the right is the functor of invariance applied to some complex, which is the injective resolution of M. Okay, so the injective resolution of M is still a resolution by G modulus. When we take invariance, again nothing happens. Meaning when we multiply an invariant by G, nothing happens.
Mm-hmm.
Okay. So and then when we take homology, again nothing happens. Okay. This is an improvised and sketchy proof of the fact that G acts trivially on its homology. And if you want a more detailed proof, it can be found in all sorts of books books on group homology. For example, in the book by Fagan and Fuchs, or in the book by Kenneth Brav. This is another good source of information on group homology. Anyway, now we understand why the quotient group G by H acts trivially on the homology of H with m coefficients, and we have a description for the second page of the Leray spectral sequence of the vibration BH, BG, BG by H. Okay. Now, Dima, Volodya, Simon, and Grisha, does any of it make any sense?
Yeah, it's quite clear.
Okay, so now we understand where the Hochschild spectral sequence comes from. Okay, and we want to describe it in the particular example where H is the alternating group A3, and G is S3, and the quotient is by 2. And we want to understand what we get as the answer. So, what do we get?
Well, I have an answer, but I don't know how to.
Well, okay. Let's try to understand the answer, and then we'll see whether or not we're able to. We're also able to understand why the answer is a square. Okay, so let's try to save the blackboard or the whiteboard again. See if it works now. Так, что давайте мы поймем, куда он сохранил. У меня такое ощущение, что он куда-то сохранил, но куда сохранил, неизвестно. Давайте попробуем понять. Сейчас, давайте скажем, сохранить в PDF. И попробуем сохранить. Вот, значит, показать вкладку. Что это за вкладка?
Ну вот это та папка, да. То есть вот сейчас вот появился PDF-файл, до этого не было.
Так, появился PDF-файл, раньше не было. Ну, да, ну, в общем, иногда такие вещи бывают, к сожалению. Так, ну хорошо. Well, let's try to. Sorry, we messed up the notes, but hopefully one can see the board in the recording. Okay, so now we want to write down this CR spectral or CR Hochschild spectral sequence for the symmetric group S3, and what's the module?
No, it's just
with trivial coefficients. Okay, so
so let me just first try the answer. We're going to see how it works.
In general, the knowledge of symmetric groups is very complicated, and on the other hand, as we will see, the homology of the infinite symmetric group is slightly simpler than the homology of the individual symmetric groups. Well, same as for moduli spaces, the homology of each individual moduli space Ng is very complicated. But the statement part is simple. Well, the same happens for symmetric groups as well. let's try to understand. Well, there's just one normal subgroup. One interesting normal subgroup, and we have this this extension. Okay. Right. Wszystko pохоже, что ужасно будет сказать. Ну, сходу кажется, что в Е2 будет что-то ужасное. Или нет? Потому что там, ну что мы хотим? Ну, там будет гомология там Z2 с коэффициентами гомология Z3.
Там еще в записках предлагалось, собственно, посчитать.
Ну, давайте поймем, как Z2 действует на Z3. Ну, понятно, как умножение на минус единицу. Well, first of all, the action of Z2 on Z3 is just multiplication by -1, which is easy enough to understand. But then we know the homology of Z by 3. Basically, Z by 3 in degrees. In not degrees, is it? Well, Z in 0, then Z by 3 in odd degrees and 0 in even degrees.
Yeah.
Okay, so what's so also what's the action? Again, it's either the trivial action or multiplication by -1. Let's see which is which. In which degree we have which action.
I'm not sure if this is an appropriate comment, but maybe it would be easier to compute cohomology, because in cohomology you also have the multiplicative structure, which comes.
It's a good point. Apparently, there is a way to compute the answer without multiplication structure, which is surprising, but apparently that's what the notes say.
No, the notes do use homology.
Oh, the notes do use homology. Maybe we should as well.
Yeah.
Yeah, because also it is like easier to describe cohomology as just a ring of polynomials truncated in generator times 3 or generator times 2.
But for cohomology, the even and odd will be interchanged. So for cohomology, we will have But still, the question is, we want to understand the action, and well, it's not a massively difficult thing to do, but still, we need to do it. So, how does Z/2 act on how does multiplication by -1 act on the cohomology of Z/3? Is it -1 everywhere or only in some degrees?
I believe that it is the change of sign of the polynomial generator, so it's -1 in degrees divisible only by 2 and nothing in degrees divisible by 4.
Well, this is another very good point. Here we use multiplication. So if something gets multiplied by -1, the square of something gets multiplied by 1, and so on. Значит, мы говорим вот что. По гомологии вот этой штуки, в отличие от гомологии, не имеет структуру кольца, поэтому значит, все определено тем, что происходит в градировке 2. А что там происходит? Ну, там происходит умножение -1. Значит, ну, градировка 4 будет умножение +1 и так далее. В градировке 6 будет S-1. Okay, so we have trivial action in even degrees and non-trivial action. Trivial action in degrees which are multiples of 4, and non-trivial action in degrees which are multiples of 2, but not multiples of 4. Okay, so we calculated the action, and then what? Well, then we need to calculate the cohomology of Z/2 with coefficients in Z. Well, the trivial with the trivial action Z/3 with the trivial and non-trivial action. Well, we sort of know. Okay, so 2 and 3 are co-prime, and as a result, the cohomology of Z/2 with coefficients in Z/3 with trivial action is 0, except in degree 0, in which case it's Z/3. Okay, this needs to be checked, but I think it is true. And well, in particular, 2 and 3 are co-prime, which means 2 is invertible in Z/3. And basically the same argument which proves that the rational cohomology of a finite group is 0 proves that the cohomology of Z2 with the coefficients in Z/3 is 0, except in degree 0. Okay, so but still this is something which is not very difficult to check directly. So Grisha and Dima, do you agree?
Yeah, absolutely.
Yes.
Okay, so now we have calculated the homology groups of Z2 with trivial coefficients and it's also right the homology with z coefficients, which is basically the cohomology of RP infinity. We know the answer, let's write it down. We have z into 0, z by 2 in all even degrees, and 0 in all odd degrees. I mean, z by 2 in positive even degrees, and 0 in odd degrees. Okay. Now, what about the cohomology of z by 2 with coefficients in the non-trivial action on z by 3? So this time the action is non-trivial. But what is the answer?
I think the answer is the same. We only have H0.
It's almost the same because we don't have H0.
Well, we have H0, but different H0 because they're trivial invariants.
Yes. So this time the answer is 0 for all I, including I equals 0. Okay. In a minute we'll see why this is true. But first of all, we have all ingredients to write down the second page of the spectral sequence. So let's do this. Well, we have the 0th row, which is z, then z by 2, then z by 2, and so on. Well, let's write it down. So we have z, then 0, then z by 2, then 0, and so on. Then 0, then z by 2, and so on. Okay, so we have the second row, and then we have, the first row is 0, the 0th row is what it says on the board. The first row is 0, and then we have the second row, which is basically z by 3, and then lots of zeros.
Yeah.
And it turns out we're in luck. All non-trivial groups live in even degrees. What does this mean? Well, this means that there aren't any non-trivial differentials. which means basically additively we get the answer.
Actually, I'm confused. Why did you change the scale of this page? Because why is it in degree 2? This Z3.
Sorry?
What?
Why Z mod 3 is in degree 2? It should be only in degree 4, because in degree 3
Yes,
we
yes,
have
I
the
mean,
change of sign in
just,
there.
yes, it should be 0.
Hold on. Oh yes, we have yes. So we have okay. So okay. So we have z by 3 in degrees multiples of 4 and 0 in other degrees. Okay. What do we have? The answer is we have z by 2 in all degrees which are multiples of 2 but not multiples of 4, and z by 6 in all degrees which are multiples of 4. Okay. Now, by the way, why z by 6? Because there's just one group, just one extension of z by 3 by z by 2. Again, 2 and 3 are co-prime, so z by 2 direct sum with z by 3 is z by 6. So this is log, pure log. So more often than not, there are non-trivial extensions. But in this case, we just for stupid reasons we get the answer just by looking at the second page of the spectral sequence. Okay. Now, does everyone agree? Does everyone agree with the second page and with the answer?
Yeah, but probably we can say something even better. We can say that it is a ring which is generated by two variables, one in degree 4 and another in degree 2. Their product is 0, and we have relation like 3 times the first variable is 0 and 2 times the second variable is 0.
Well, let's see. Yes, I think you're right. So we also have the product structure. Basically, okay. So let's there is a unique element which generates H2. Now, in degree 4, there is a unique element of order 3, up to side. Let's take the first element to be the first generator and the second element to be the second generator. Then so the product is 0. Well, the product has the product lives in in the quotient group of z by 3 tends as z by 2, but z by 3 tends as z by 2 is 0. So the product is automatically 0, again for stupid reasons. Okay. Now, so yes, it looks like we have the answer even multiplicatively. Namely, the answer is we have two generators and very simple relations. Namely, the square of one generator is 0, and 3 times the other generator is 0. Okay. Now, said, it's a stroke of luck. Most of the time, none of the tricks we've just used work. Okay, does everyone agree with the answer? Okay. Dima, Grisha,
Yes.
Volodya.
Yes.
Okay. Now, I think we should finish. We should finish soon. Is there any other examples we wanted to calculate today?
Well, I don't really have anything else.
Say again?
I don't have anything else.
Okay. So let's just see one more thing, which is basically what we used to compose this. So we okay. So suppose we have well, G, a finite group. And M, a G module. And suppose timesing by the order of G is an invertible map from M to N. Again, my claim is that the okay the positive the homology of G with the M coefficients is 0 in positive degree. Now, how to prove this? Let's see.
I guess this is just equivalent to saying that invariants are an exact functor, and it is exact because we have the averaging operator, which makes it a retract of the module itself.
Okay, so we have a local system. Let's call this map P. We have a local system. I don't know. Let's call it M. What do we have? We have the pullback, which is which is a trivial local system on EG because there aren't any other local systems on EG. EG is contracted. Okay, now now I want to show that the map the map P of the star is an isomorphism, and well, basically this this will prove the claim. Let's see. Well, to prove it's an isomorphism, I want to construct an inverse, and the the inverse is the inverse is okay. No. B, G. Okay, now let's see. There's not enough room.
I'm sorry, can I ask a question?
Sure.
Is it true that the retract of an exact functor is an exact functor?
Don't know.
Because if it is, then obviously the functor of invariance when the multiplication by the order of G is invertible is a retract of the identity functor. Because invariants are the image of the projector operator, which is constructed by averaging over the action of the group on the module.
Yes, I agree. So what Grisha is saying that when the image of G is invertible, then there is a splitting. LG is the sum of so the sum of m output m m plus what?
We can identify the second summand with the co-invariance, I guess, but
let's see. No, not it. Okay, so well, I think what Grisha says doesn't need well. The first statement about functors may or may not be true. It's not very difficult, but I don't know. But let's look at the direct image of the trivial no, sorry, of the trivial so let's look at the direct image of the trivial module on EG. So my claim is that this thing is the same as M, and plus plus some M prime, and so the the cohomology of VG with M coefficients is the same as the cohomology of BG. Sorry, cohomology. BG. Well, this is by general nonsense. Okay, and this is the same as the cohomology BG M. Plus something. But this is automatically zero in degrees, in positive degrees. And hence, so is this. Again, this is an improvised group. But the essential part is this. The direct image splits as the module we had plus something. Okay, and by the way, what is what do we have? What do we have here? What is M prime? Let's. Okay, let's think a little, and then we'll finish. Let's think for 3 minutes, and then we'll finish.
Yeah, yes, I said something stupid about identifying M prime with covariance. What I meant to say was that M prime is what is sometimes called the submodule of purely non-trivial representations, meaning that basically the description is that it is an internal of the averaging operator. So when you like sum over action of all.
Yes, something like. Okay, so. Let's well. First of all, let's make sure we. Okay. So this time we probably do have a copy of the notes. Well, only 3 pages, but it's better than nothing. Anyhow, let's try to think of it. Okay, so I have a trivial. I have a trivial. Sorry, but I have a trivial local system on EG with stroke M. I want to push it forward. What do I get? Well. I get the group ring of Z by G over Z by G. No. Okay. Okay, is this the right answer? With the diagonal action of G. it looks like yes, it looks like this is the answer, and I want this to be n plus prime. And okay, so this thing does contain M as M tensor 1. And now I want to construct a projection of this thing onto this, and here. Does this make sense? Okay, it doesn't make sense. Okay, let's erase this part and leave this this as an exercise. So the direct image has this form, and what is in prime we don't know, but it's easy enough to figure out or to find in some book about group homology. Okay, so let's save the notes. Okay, is there anything else we want to discuss today? Well, it looks like the answer is there. The default plan for next week is that I will continue talking about the proof of the Madsen-Weiss theorem, and if someone wants to give a talk, please let Chris and myself know.